Welcome to the lecture series of Basic Electrical Engineering. The subject code is ECE 101. The topic of today's video lecture is practical transformers. As in the previous video lecture, we listened ideal transformer, in which we discussed the working of ideal transformer and its phasor diagram and the EMF equation of a transformer. So before moving to the practical transformer, I am giving a review of ideal transformer. Basically, it is nothing but a transformer which has 100% efficiency. In this transformer, there are two purely inductive coils. So this has no iron loss, no copper loss, as well as there is no I square R losses. Also, this is no ohmic resistance drop and no leakage drop. Hence, this is the concept of ideal transformer. As shown in this figure, we are having the figure of ideal transformer in which we are having this primary windings, secondary windings, the induced voltage on the primary side, induced voltage on the secondary side, the current on the primary side, current on the secondary side, and phi is constant, and V2 upon V1 is equals to I1 upon I2 is equals to N2 upon N1. So this is the conditions of the ideal transformer. Before moving, there is the difference table between ideal transformer and the practical transformer. First of all, it has 100% efficiency, but practical transformer efficiency is below 100%. There are no losses in ideal transformer, but practical transformer has some losses, negligible losses. It is purely inductive material is used. It is two purely inductive materials are used. Here we are having two inductive materials. It has no I square R losses. It has I square R losses. It has no iron losses. Ideal transformer has no iron losses, but practical transformer has iron losses. In ideal transformer, there is no ohmic resistance drop. The voltage drop across in the case of ideal transformer is 0, but in case of practical transformer, we are having the ohmic drop. There is no leakage drop in the case of ideal transformer, means there is no phi 1 or phi 2 flux produced in the ideal transformer, but in the case of practical transformer, we are having the leakage drop, that is, we are having phi 1 and phi 2 flux drop in the practical transformer. Then in its ideal condition, it is in ideal conditions, it is in its practical conditions, it has no use in practical condition. This ideal transformer is only for the study purpose. It is not having any practical relevancy, but it is used in actual practice. It is used for the commercial as well as for the manufacturing purposes. Now, practical transformer, what actually the practical transformer is. A practical transformer differs from the ideal transformer in many aspects. The practical transformer has iron losses. As in the case of ideal transformer, we said that there are no iron losses, but practical transformer has the iron losses. Then there is the winding resistance in case of practical transformer, but in the case of ideal transformer, we are saying that there is no winding resistances. And in practical transformer, magnetic leakage giving rise to leakage reactance. But in case of ideal transformer, there is no magnetic leakage and there is no there is no rise to the leakage reactance. There is no leakage reactance in case of ideal transformer. So this diagram shows the practical transformer in which we are having these two components extra. Here this is R1, the resistance. Here we are having the voltage drop across R1, and this is the reactance X1. These two are on the primary side, and R2 and X2 are on the secondary side. Now we will discuss why we are having this R1 and X1 on the primary and on the secondary side. First of all, we will discuss the iron losses. What do you mean by the iron losses in the practical transformer? Alternating flux phi passes through the iron core. It creates eddy current and hysteresis losses in it. Two of these losses called iron loss or core loss. Iron loss depends upon the core volume. Basically, the losses due to iron losses occur due to the core volume. Means core volume is as if I am telling you this is the core. Here we are having the windings, primary and secondary windings. This is called the core. So iron losses depend upon the volume of this core, then the supply frequency and the maximum flux density. Maximum flux density is Bm. As we know that phi m is equals to Bm into A. Flux density into the area, core area. So if this is maximum, then we are having the core losses. Magnitude of iron loss is very small in practical transformer. In actual practice, its magnitude is very small in practical transformers. Then winding resistances in transformer. Primary and secondary windings made with copper wire. The windings we are having on the primary and on the secondary side are made up of copper wire. Every conductor has its own resistance. So primary and secondary side have resistance. As I have shown you in the previous diagram, we drawn here a resistance and a inductance on the primary side. So this resistance is due to the windings have some resistance. Primary and secondary side have resistance. So this primary resistance is denoted by R1, and the secondary resistance, this resistance is denoted by R2, and are in series with the respective windings. In series with the respective windings. So this is the explanation why we are having this R1 and R2 in the practical transformer as shown in the figure. Due to winding resistance, when current passes through the winding, when we are giving the supply voltage here, the resistance current is flowing in the primary side. There is voltage drop due to this resistance, IR1 voltage drop in the resistance, and it causes the power losses. It affects in the power factor. It also affects the power factor. Hence E1, the induced voltage across the primary, is less than the applied voltage. So this is the explanation of the condition why E1 is less than V1, because there is a voltage drop due to the resistance of the windings. E1 induced voltage is less than the applied voltage. Similar is the case that V2, the voltage due to this induced EMF, mutually induced EMF E2, V2 is less than E2 because E2 is produced because of E1. So next is this diagram shows now in winding resistance. I have explained why we are taking this R1 and R2, and the voltage drop here is IR1, here IR2, and because of this IR1 we are having the power losses on this side as well as on this side, and I have given you the reason why E1 is less than V1 and why V2 is less than E2. So next I will explain you Leakage reactance in the transformer. Common flux phi links both primary and secondary side. Primary current I1 produces individual flux phi 1 in the primary side, and secondary current I2 produces flux phi 2 in the secondary side. These two fluxes are not common in both sides. Hence, flux phi 1 and phi 2 are known as leakage flux in the transformer, as shown in this figure. Here on the primary side we are having the phi 1. This is the leakage flux because of this current I1, and phi 2 is the leakage flux on the secondary side. So, and this is the flux phi which is linking the primary and secondary side. So this is about this. Now the leakage flux path is further is through the air mainly. The leakage which occurs due to phi 1 and phi 2, the path is air. The effect of primary leakage phi 1 makes an inductive reactance X1 in series in primary winding, and in secondary leakage flux phi induces an inductive reactance X2 in the series with secondary winding, as shown in figure. As we are having the primary side, secondary side, here we have the resistance, and I'm talking about the X1. Because of this leakage flux phi 1, we make an inductive reactance X1 in series with the primary winding. So that is why this inductance is in series with the primary winding, and here X2 in series with the secondary winding. Primary leakage flux phi 1 induces back EMF E in the primary winding, and it is alternating 1. Then primary leakage inductance L1. So here the formula, how we find out the primary leakage flux. L1 is equals to number of turns into phi 1 primary leakage flux upon I1. Then primary leakage reactance X1 is given by 2 pi f L1. L1 value we will take from here. In the same way, secondary leakage reactance L2 is equals to N2 phi 2 upon I2. N2 is the number of the secondary sides, phi 2 is the leakage flux due to current I2, and upon I2 secondary current. So X2 leakage reactance is given by 2 pi f L2, and L2 is find out from this value. So no power loss occur due to the leakage reactance. There is no power losses because of leakage reactance, but it changes the power factor. Power factor means cos phi. It changes the cos phi. Power factor is equals to cos phi. As well as there is voltage loss due to I into X. The voltage drop in the reactance is changing, and the power factor is changing. Flux leakage is quite small, about 5% of mutual flux phi. If mutual flux phi, total phi is 100, then the leakage flux is very less, means phi 1 is less than 5%, and we can neglect it or we can avoid it. Then we are talking no load practical transformer. This diagram shows the no load. No load means that on the secondary side we are not having any load across this secondary side, and on the primary side we are having the applied voltage V1. A practical transformer shown in figure, there is no load in the secondary side. It is open circuited. When AC source is connecting in the primary side as shown here, a small current I naught, this current I naught flows through the primary. I naught means I naught represents no load, when there is no load on the transformer. It occurs a very small amount of copper losses and iron losses. Because of this small current, copper losses and iron losses in the primary side are very small. So that primary no load current I naught is not equals to 90 degree, but I naught is less than 90 degree behind the applied voltage, but lags by angle phi naught less than 90 degree. So because there are the small amount of losses, very small amount of losses, copper losses or iron losses, the primary current is not at 90 degree but less than that. No load input power W naught, it is denoted by W naught, is equals to V1 I naught cos phi. In the primary side, I naught get two components. This is very important. I naught current is divided into two parts, IW and IM. IM is the magnetizing current and IW is the working current. We are discussing one by one. The component IM is known as magnetizing current. Magnetizing component, this component produces mutual flux phi in the core. As we know that we are having the here we are having the phi, so this phi is because of the magnetizing current IM. Fine. This component produces mutual flux phi in the core. IM lags behind V1 by 90 degree. In actual practice, IM lags behind V1 by 90 degree. IM is equals to I naught sin phi. Then next component is IW, which is known as active component or working component. The component IW is known as iron loss or active or working component. It is in phase with the applied voltage V1. It supplies a very small primary copper loss and iron loss. So IW is equals to I naught cos phi. So this is for magnetizing current and this is for the active or working current. Practical transformer on no load phasor diagram. This shows a phasor diagram of the practical transformer. Now look into this. IM is in phase with phi and this current I naught is divided into two parts, IM and IW. So it is clear that I naught is the phasor sum of, I naught is produced phasor sum of IM and IW, and I naught can be given by this formula. I naught is equals to under root IM square plus IW square. No load power factor cos phi, this is cos phi, is equals to IW upon I naught. At no load practical transformer, primary copper losses I naught square R is very small and this loss may be neglected. Hence, primary no load input power of practical transformer is equal to the iron losses. No load input power W naught is equals to iron losses. So the power on the input side is equals to the power iron losses. As primary loss in practical transformer is quite small, the losses occurs on the primary side of the practical transformer are small, it can be written as V1 is equals to E1 and there is no load in the secondary. When there is no load in the secondary, E2 is equals to V2. So this is the condition. The phasor diagram of practical transformer on no load. Primary small current I0 is the phasor sum of Im and Iw, as shown in the previous diagram also. This is a phasor diagram. Primary no load current I0 lags by V1 by an angle phi naught which is less than 90 degree. This shows a comparison of phasor diagram of practical transformer under no load and the phasor diagram of ideal transformer under no load. As shown in this diagram, Im is in phase with phi. Same here, Im is in phase with phi. Here V1 is equals to E1 negative. So that's why we are drawing it here on the opposite side. And because in the case of ideal transformer, V1 lags behind, Im lags behind the V1 by an angle 90 degree, or we can say that V1 leads Im by 90 degree. But in case of this, V1 and the angle between V1 and Im is angle phi. As here this angle phi is less than 90 degree. So this is the reason we are taking here. This is our I0 and this is IC, IW we can write, and this is Im. And the summation of this is called I0 is equals to under root Im plus Iw square. So this is the comparison of the phasor diagrams. Now coming to the next, equivalent circuit of a transformer. When we are talking about the no load equivalent circuit, as in the explanation I have told you that this I0 is divided into two components, IC or we can say Iw. Both are the same things. Iw is the working component, IC is the core losses or the current due to core losses. So Im here current I0 is divided into two parts, Iw and Im. So this is R0. R0 is the resistance due to primary windings, and X0 is the reactance on the primary side. R0 is given by this formula. R0 is equals to V1 upon Iw. Here you can write Iw. And X0 is equals to V1 upon magnetizing current. This produces the flux in the core, and this causes the losses. So Im is equals to I0 sin phi naught, that is called magnetizing component. IC or Iw is equals to I0 cos phi, that is active component or working component. Both are the same things. So this is about the equivalent circuit of a transformer on no load. When someone say what do you mean by the no load equivalent circuit, you have to draw this resistance, inductance and the supply. Here I0 current that divides into Iw, and here Im. Magnetizing current always on the reactance side, Iw on the resistance side. So this is about the equivalent circuit. Then moving to one practice numerical. A transformer takes a current 1.2 ampere and absorbs 128 watt when primary is connecting to its normal supply of 400 volt 50 hertz, the secondary being on open circuit, find the magnetizing and iron loss currents. So what is given to us? 128 means W naught, the power is denoted by W naught is equals to 128, and the current is given to us, current I naught is given to us, that is 1.2 ampere, and V1 is given to us, V1 is equals to 400 and frequency is 50 hertz. So no load primary current, primary power, we know that this formula W naught is equals to V1 I naught cos phi. From here we can write it W1 upon V1 is equals to I naught cos phi, this equation. Then iron loss component IW is equals to, IW क्या होता है हमारा, I naught cos phi. So we can replace this I naught cos phi with this value. We can write it W naught by V1. Now we know the value of W naught is 128, V1 is 400, and we calculate its value, it is 0.32 ampere. So iron loss component is this much. Now no load current, we know this formula, this is the standard formula, as this is I naught and it is the summation of magnetizing current and the working current. So from here we know the value of I naught, we know the value of working current, iron losses. So we are finding the magnetizing. Im is equals to this formula. Now we put the value of I naught, that is given to us 1.2 ampere, and IW we calculated here, this is 0.32, and we put into the formula and we will get this. So this is the Im, magnetizing current Im is equals to 1.16 ampere. So this is all about your today's lecture. Hope you understand. Thank you very much.